I'm Dave Robertson. I'm the head of College of Science and Engineering, and so it's my privilege just to do the opening of this event. And of course, it's power electronics, as the title says. I know almost nothing about power electronics. I used to believe that that was just something that happened mysteriously on my mobile phone and everywhere else. Actually, until recently, actually, funnily enough, actually last week I had a visitor from the Faraday Institute, and he's explaining why we may or may not have a car industry in future, and it all comes down to power. And power electronics and all that, because of the nature of automotive engineering in future. So you do start to take things more seriously when expressed in those terms. So I just want to say a few biographical notes, and then you can get on, Steve. So Steve's our chair of power electronics, of course. First degree in Loughborough, I believe, in '88, and then off to the Electricity Council R&D Centre in Cheshire. So not academic. Then academic career in Heriot Watt in 1990, I believe, PhD in electrician there. And then 2005 to Strathclyde off to the west to become their head of power electronics research, 2010. And then continue in 2017, IEEE Industrial Applications Society Distinguished Lecturer Program, which is a feather in your cap, and onwards and forwards to international fame. For example, on the automotive side, I believe the UK-China Consortium of Research into Electric Vehicle. I don't know if you're going to be talking about that, but those sorts of things. I'll stop now with those short comments. Kahura will pick it up at the end. For now, take it away, Steve.
Thank you very much. And welcome, everybody. Looking around the audience, I seem to have captured a very large proportion of the Scottish power electronics community. Hopefully this won't be too simple for you. If you've got any nasty questions, I'll be really happy to receive them at the end. I'm looking at you, Craig. So, welcome to what's hopefully going to be an interesting and entertaining talk about power electronics, ubiquitous and, in my opinion, fascinating technology which exists almost everywhere. We'll endeavour to answer what it is and why do we need it, because most people don't know what it is even though they're using it every day. And as one of my colleagues in the power electronics group here said, no one really cares about it until it goes bang. When it goes bang, it's quite exciting. As anyone who worked on the Hunslet Berkeley locos back in the 90s can testify. So, when I started this, I thought, what defines power electronics? I'm not going to read all of these out. There's various things I culled off of the internet, but two things struck me. The underlying aspect is its solid state control of the conversion of electric power, and it's control using switches. More of that in a little bit. The other interesting factor I pulled up, which is possibly, in my opinion, an understatement. 80% of the power generated, processed, recycled, really used, passes through some form of power electronic system. We use this every day without even realizing that we're using it. So where do we use power electronics? When we talk about power electronics, we're going to talk a lot about switches. Now, if this works. When we think about switches, we think about something we can turn on and off. The simplest thing we can do. If we were 100 years ago, probably that's what we did. We turned on a switch, it turned on a light. We turned on a switch, it made a machine spin. But that machine wouldn't spin at a nice controllable speed. It would just spin. If we wanted to control its speed, we had a gearbox. If any of you worked in lathes in your workshop training back in the 80s, you'd have probably had a little cover you took off and you changed some rubber bands to change the gearing ratio for it. So switches evolved. What can you take next? You can add a little bit of control. That's a relay. It's basically a switch with an electromagnetic coil in there to make it open or close. The key thing that we made a difference there is we've got some controllability. An electrical signal will make that switch open and close, so another relay could control the action of this relay. And we started to build the very first kind of computer or control using that very same type of technology. In fact, some of it was still in use back in the 80s in some of the plant that I worked on. But it started to allow you to build up more complicated systems. But the real change happened when we started to move our switches into solid state. That allowed us to bring really the microelectronic revolution, which we're all really aware of. It's really permeated into really every aspect of our civilization and society. Now, when we think about digital and the digital age, we're thinking generally about the processing of communications and data and information and performing sums. But there's another really important issue, and that is control of power. Because without controlling power, we can't actually interact with the real world. A few things there. We talked about automotive, but if we want to control traction, we need to control the motion. We need to control the torque and the speed of that machine. And we need to regulate the electricity that's put into that, otherwise it's not going to work. It allows us to capture clean energy. Clean energy isn't naturally suited to a conventional generation system. It powers all of the little gadgets that we hold. We have a battery inside our mobile phone and a multiplicity of different voltage levels which drive different components of that phone, from the high power analog, which is going to drive the audio, to the really low voltage fast microelectronics, all from one battery, a little mini power system just inside one block. But all of that power system relies on power electronics to do the conversion. It even comes down into the simple things which we'd take for granted that would have once just flicked on and off with our switch, like our lighting and our heating. Heating is going to be moving to heat pumps. Lighting is now mostly or largely LED if it's efficient. So it comes into everywhere. And just kind of capturing that, we've got, I'll bring this back up again. On our input side, PV, wind, offshore wind, transportation is going to become huge. We're going to have energy storage, battery banks. We're going to have power networks, again relying on power electronics, and then to cross to a multiplicity of loads, all of which are going to be increasingly dependent on solid-state power conversion. And what allows us to do this? We'll see a little bit more of these again as we go through. Solid-state switches. It's not changed. Right, that is what's called an IGBT, insulated gate bipolar transistor. To those of you that don't work in the sector, that's not going to mean anything, but it is a solid-state switch. This one is capable of switching 1.6 kilovolts and 600 amps. If you do the sums on that, that little device is capable of controlling the flow of hundreds of kilowatts. It's the type of power levels that are going to be talking a pretty large traction motor or a small wind turbine. Not only is that a switch, that switch can operate many thousands of times per second. And that opens up the ability not just to turn things on and off, but to control and modulate the power that goes into those devices. So why is this becoming so big? And we're going to go on to some of the background. Why is power electronics going to become such a really big part in our industry and in our lives? And it all comes down to energy. The way we're generating and using energy is really, really changing. It's going to change even faster, and as it changes, it's going to build a bigger market and demand for power electronics engineers and a market for the devices that we use. And we can start to look at what happens. This is going back to the old days. We generated our power from rotating turbines. We regulated the speed, and they produced a fixed frequency AC grid. We stepped up our voltage using transformers, because we can do that with AC, use that to move long distance, then step down and used it in a lot of loads, many of which were designed to plug into your 240 volt supply and run quite nicely from that. That's probably 1950s world. Let's go forward to what we're seeing now. This here is starting to come in. We're talking gigawatts of power associated with wind. We're talking a significant amount of PV and a really big growth of area in offshore wind, all of which are not naturally 50 hertz. They're not regulated by the energy that we put into the machine. They're regulated by how it can capture that energy. And they have to adapt their set point to actually capture the maximum amount of energy from what's available. Our AC transmission may now actually be supported by HVDC, a technology which allows us to transmit power efficiently over really long distances and is essential for connecting offshore wind or for having international interconnectors to allow energy pooling. Coming down through our system, we're going to have some embedded generation. Again, likely to be PV, likely to require power electronics, and we're down to many other systems as well. Here we've got storage. So we're moving towards that. That's sort of schematic, but let's look at a bit of the problem that we've got faced at the distribution end. I talked about the way the loads are changing, where we use it. Generation, we can understand where, we start to understand where it's coming from, but everything we've got in our house is no longer a nice fixed AC load. Even 10 years ago, maybe 12 years ago, we would have seen most of our lighting from incandescent bulbs. It's now going to be LEDs. LEDs are naturally require DC. The heat in your house, not changed so much. If you've got a storage heater, probably still a heater element. But if we move to heat pumps, we're going to need to have variable frequency AC to control the compressors. In motion, we're back to sort of my nice picture of an ancient lathe. That just turned on and span the motor on that. If we wanted to control the speed, we changed the drive shafts to give us a different gearing ratio. Nowadays, we're moving towards electrically controlled traction and really advanced robotics, which require precision control. And in your house, 1950s world, you probably had your TV, the only electronic gadget that you probably had. Nowadays, you've got a multiplicity of systems, all of which require to have power electronics. And if you wonder why your power supply for your laptop or your mobile phone charger is much smaller today, that is because people have got better at building the power electronics that's in it. But more change is coming. This, and I'm afraid this hasn't reproduced as well as I would have liked, this gives the energy map of the UK. And this is a snapshot in 2009. There's some bits to pay interest to. This is our stream that's coming into electricity generation. And we can see here a massive amount of coal in black and a very tiny amount of renewables coming in. Two things to bear in mind: large amount of reliance on fossil fuels, and also you've got these other streams coming in. You've got gas and you've got oil, and they all come to direct fossil fuel burn at the end. Direct fossil fuel burn is used for most of our heating, it's used for most of our transport. Fast forward by 10 years. Right. Energy mix now. Massive, impressive reduction in coal. We've got a pretty impressive increase in renewable generation, even given the original starting point 10 years ago. The things that we still see not change much is our other direct fossil fuel burn. And we're going to have to move that from this direct use of fossil fuel power to electricity if we're going to satisfy our need for clean energy. And that comes in particularly in the automotive sector, where we're going to look to electrify or clean the energy that we use. What's going to be happening? Emission reduction. Targets. It's all really driven by targets. If we weren't interested in targets, we weren't interested in the environment, very little of this would be happening. We're talking really ambitious targets to get rid of CO2. And where's that energy going to have to come from? In the absence of a massive nuclear rebuild program, that's going to come from renewables. At present, electricity accounts for 30% of UK end use. We're going to have to swap that to electricity. Electricity also provides the transmission vector of the majority of these clean resources. So we're going to have to generate it, we're going to have to move that energy using power electronics. That takes us into the really big stuff. What can we say? Even if we manage to make big hits in the efficiency, which are probably there, EVs are more efficient than petrol-powered vehicles. Electric heating could be improved, or heating could be reduced by insulating houses, but we're still probably going to see a big rise in demand for electricity over our clean energy grid. But we're sort of getting there. This was some figures from recently. 36% on a single day was produced by Britain's renewable resources. We're seeing massive investment in the sector. And onshore wind in our Western environment is currently competitive. It's no longer reliant on subsidies. So we've got these drivers. We've got these drivers wanting to change the way we use and generate electricity. Now we start to build up what goes on inside what we can term power electronics. And it was really quite simple. Our first guy, again, is our switch. Our switch is what lets us do everything. And it's the fact that we've got this efficient bit of semiconductor. Like any other switch, it's got negligible losses when it's on, and it's got negligible losses when it's off. On, because you've got practically no voltage drop across it. Off, because nothing's flowing through it. Same as any switch, but really, really fast. So our principle here, we have a control system. Let's get some dot cam again. Cross here, big meaty power connections. Input to the device, output to the device. And it can support a voltage across it. I have it turned off. It's going to support up to 1.6 kV without breaking down. I'll apply a control signal to that, and it will therefore turn itself on, and it will conduct. In both of these cases, it should be efficient. And it can be huge, like the one we've got up there. It can be slightly smaller. And these are the type of things we play with in the lab. Or it can be really tiny. It can get tinier than that, but that gives you an idea of the smaller size. But they all perform the same purpose. One of the key things about them, and we're going to look at this later, is the only time when its efficiency breaks down is when you try to transition it between on and off, because nothing happens instantaneously, even in these fast devices that can switch in tens of nanoseconds. The types of rating that we can achieve, up to 6.5 kilovolts for high power applications. Switching speeds can be really fast. If we take the really modern devices, you can be switching 1.2 kilovolts at about 100 nanoseconds. And the voltage drop is low. A device that can block 1.2 kilovolts only has a 1.3 volt, a fraction of that across it when it's on. So you're not losing much power actually in the device. It's significant in terms of heating the poor little bit of silicon, but it's not significant in terms of the total power throughput that we could get. We put that together with other bits to make a system. First thing that you might come across, a resistor. Doesn't do very much that's interesting, it just burns power. It's normally smaller than that, but this is nice and visual. We've got an inductor. Inductor, electromagnetic component. A lot of copper windings round a core. It forms another part of the switching circuit, and it has some interesting effects when we start to build up these circuits. Still quite, and what you can remember is it restricts the flow of high-frequency electricity, namely high-frequency electricity doesn't want to pass through it, and it allows low frequency to pass through. We also have capacitors. This one's a bit more visual. This is a huge one. They're normally smaller than this. Again, we like playing with big stuff in the lab. What does that do? It can act as a energy reservoir. It stores charge. But it also has another effect on the electricity. It wants to pass high frequencies. High frequencies don't generate much voltage across it. And it wants to restrict low frequency. Low frequency causes it to charge up and block the voltage. And we put those together effectively to increase the time constant of our electrical circuit so that we can apply our modulation techniques. On top of that, we need some other stuff. And if I find, no, I've forgotten to bring it. Sorry. On top of that, we need to have control. We need to have control electronics, effectively embedded computers, which measure all the quantities associated with our power converter and issue the control signals to the device. We're going to have transducers. And as we're often operating at high voltages, these need to be isolated. And they need to feed appropriate signals into this control electronics to make it work. Last of all, as an interface between the intelligent parts, we use things called gate drivers. We need to be able to push some current or some voltage onto that device to make it switch. And that allows us to do some clever things with how it behaves, because we can start manipulating its switching to be more efficient or more benign. You start putting the whole lot together, and you end up with a system. This takes us to a arbitrary power conversion system. We have a source, we have a load. The source's electrical characteristics isn't going to be compatible with the load. It's very unlikely to be. So if we take something like our automotive system, that would be a battery. Our battery is going to need to regulate the power that's taken out of it. Battery is DC. We'll probably have a DC to DC converter there. That's regulating the power to the battery to match the power that we're putting into the load. On the other side, I've got a machine. Machines rotate because we generate rotating electromagnetic fields in them. And those electromagnetic fields that exist in them are caused by the applied voltage. If I want to regulate the speed of that machine, I have to regulate the frequency and the magnitude of that applied voltage, otherwise it doesn't spin. So there's no point here connecting it to DC. Unless we had a primitive DC machine spinning at a fixed speed, it wouldn't work. So all that block there relies on having semiconductor power processing to perform the energy conversion. Around that, we need to wrap system measurements, control interfaces, transducers and gate drives, a whole range of light electronics just to get the system to work. And then behind that, we're going to have some kind of controllers. They're going to perform functions like maximum power point tracking. It's going to be grid synchronization, if it's a generator, of controlling a voltage or power control to other loads. So for power electronics, this is why we find it so difficult to get postgraduates to come and work in it. There's very few areas which require you to have understanding of what the machine wants, right the way through to be able to program useful code or to design a power converter, and then to be able to wrap this control around it to make the whole thing work. Easy in simulation, but as any of you sitting sort of round about that quarter will know, really hard to make it happen for real. And this is the kind of thing it starts to look like. That's a very high frequency silicon carbide DC to DC converter, the kind of thing that you might have tucked inside your car to regulate battery charging. Switching about 70 kilohertz, a high-tech transformer, gate drives that can switch the devices in about 100 nanoseconds, achieving that high switching frequency. And interestingly enough, although on that build we bought the most expensive gate drives, the ones designed to work specifically with the fast silicon carbide devices that we were using, they tripped out every time we tried to make it work. We had to wire out most of the ancillary safety functions before those things would work reliably. And that's for a gate drive which is designed specifically for that high frequency application, which starts to give you an idea of some of the practical problems that we come across. So where do we use power electronics? Well, everything requires to be controlled. And now I've got a nice example here for those of you who have not come across any power electronics at all. Jake, I'm looking at you. Let's take us back into 1950s world. One of the few things that we might have got that we want to control is our oven. We want to heat that oven up to a reliable temperature. So how can we do that? Well, what is our oven? Our oven's basically one of these. We stick current through it and it heats up. And now we've got some maths. So the heater, the power of that heater is given by the current squared by the resistance of the heater. That's the amount of electrical energy that's turned into watts and turned into heat. And my current is given by my applied voltage divided by the resistance. So we can see that if I can control that current, which is reduced by the resistance, I can control the heat. So how might we control that? So let's take a simplistic idea. We take a variable resistor. I put a resistance in series with that, and my current is now the input voltage divided by my added resistance in RH. But I've now got controlled output here. My current goes down, but a portion of that current is burnt up in this resistor, so I've got a big loss. And if you do the sums for that, at half power you're losing 30% of your energy into that resistor. It's not a good way to do it. It's not a good way to do that, but strangely enough, if you'd been controlling the speed of a DC motor, probably about 30 years ago, that's how you'd have done it. You'd have had a big resistor bank and you'd have flicked in those resistors to control the speed. And it was done a lot because DC motors were about one of the few things we could actually control reasonably well. How might we do it more efficiently? And this is how it's done. We've got our little thermostat. Our thermostat is an intelligent switch. You could think about it being a really primitive power electronic device. So when the switch is on, the device passes current, the heater heats up, but when it's off, I've got no current flowing through there, so I don't have any power. If I control the average power to the heater, it's a ratio between the on time, so that should be T on, not T off. It should be the ratio of the on time to the total time between pulses. So I've got a means of controlling the average power. And that's what our thermostat does. Come on. Yeah. So essentially, device turns on, temperature builds up, we trip out the thermostat lets it ramp down, and it comes back up again. So we can have, and because our oven is a big thermal mass, it doesn't respond to these individual pulses, it responds to the average. So it hovers around that temperature, and we've got that temperature control. And because it's so big, our switching frequency is really low, so we can use a mechanical switch to do it. So that all works in that case, but we've got an efficient way of controlling the heat because, come on, go back, that's it. Because when this switch is on, it's not like the resistor. I'm not burning power in that switch. The switch is making contact, the two contactors are closed, and I'm not burning any power. I turn it off, I've got no current flowing through the switch. And it's not conducting, so it's not burning power. So we've got an efficient way of controlling power throughput. But we'd like to think about extending that. And we need to think about the needs where we need to do that. And the reason we have to do, and I've touched on this before, is that electricity isn't the same in all cases. So we've got alternating current. That's what comes out of our generators that we've got today. We can convert it to a variable magnitude, and that's one of the few things we could do before power electronics came on the scene. We could use transformers to step up our voltage. We don't need to convert it. The reason we might need to convert it is we're thinking about our new types of source. Batteries, PV, fuel cells, they're all DC. They've all got a fixed DC voltage. So if we want to charge a battery, we've got to convert from the grid to DC to charge that battery. If I'm taking a PV panel or a fuel cell or a battery and I want to connect that to the grid, I've got to change that DC to AC. Let's go from our battery now. Let's imagine our battery is being charged or is supplying power to a low voltage power supply. It's going to be present in your car, the need to do that. You've got 800 volts, 400 volts inside your main traction battery. You need to have maybe 12 or 24 to power your ancillaries. Across on the other stream, again, we've got variable frequency AC that we may require. So we take that fixed frequency 50 hertz, and I need to be able to change that to variable frequency. We need to change between DC and AC if we're changing from a battery to variable frequency AC. So all of those things need us to be able to take one form of electricity and change it into another in order to make that system, which we're seeing is changing, work. And it requires something clever to do that. And one of the biggest drivers, and probably the area that we're probably the biggest market because all our energy is going to have to come through something like this in the future, is that clean energy requires electronics. And that's not just clean energy from renewables, it's clean energy, it's being able to use that clean energy to do things that are useful. So, how many of you got solar panels in your houses? Judging by the audience, I suspect most of you know how they work. PV, we've got an array of semiconductors. Incident light on those causes them to start to generate current, and that's going to be a DC current. Now that DC current has to be processed because the characteristics of your PV panel change with the amount of illumination. Here's a plot of the voltage across your PV panel to the current, and the power that you're going to get out of it is the product of these. If I don't draw enough current out of it, I'm sticking down here. I've got lots of volts, no current. If I start drawing more current out of it, my volt starts to collapse. If I keep drawing more and more and more, I come down to here. I take too much current out of it, my voltage collapses, and I get zero power. If I can track along this line here, I get the maximum power out of it. So this guy here is making sure that we harness that renewable energy from the PV panel and get it out, get the maximum power to come out of it. That captures our energy, and it's going to pump that energy onto an intermediate DC link, a capacitor. One of these guys, or its big brother. And that's going to be soaking up charge, and its voltage is going to be increasing. But we need somewhere for it to go. And if it's connected into your house, it probably needs to go into AC. So we're going to be measuring this voltage here, and we're going to be using that voltage to tell us how much power to squirt onto the AC side. But if I'm going to actually control that, I need to be able to regulate this voltage. I need to regulate this voltage so that it's in phase and in frequency with the grid. So we need to measure those two quantities. It needs to measure its current so that it can measure the power it's pushing out, so that it balances the power coming in there with the power that it's pushing out. So you've got this system which allows us to capture this nice renewable energy, but it's highly reliant not just on the power electronics, but also on the control that makes it work. And this is subtly different from anything that's come before. Our big generators, they were governed principally by the laws of electromechanics. You could predict what they were going to do. This is governed by how I've designed the converter, but more significantly, it's governed by the guy that wrote the software which tells the converter what to do. If he's got it wrong, or if he hasn't foreseen something, or she hasn't foreseen something, they haven't foreseen something, it's going to go wrong. The same thing goes for wind. Wind. The energy you get out of a wind turbine is dependent upon something called the tip speed ratio. It gives us a measure of the incident wind speed and the speed at which it's rotating. If you want to keep that tip speed ratio around about its optimum value, and then you get most energy out of it. Now what does that mean? If the wind turbine's operating with most efficiently, at low wind speeds it's going to be rotating slowly, and at high wind speeds it wants to rotate fast to get the maximum energy out. Now that's not compatible with our old style generators. Although this is a nice rotating machine, it looks a bit like a conventional generator, but it's not fixed speed. It's not regulated by a governor that's squirting the wind onto it or the fuel onto it to make it spin at a constant speed. It's changing its speed because it has to get the energy out. So we need to be able to generate variable frequency AC here. And again, the principle is the same. We've got something here which is optimizing the energy capture. It's measuring the quantities of the wind turbine, it's synchronizing its signals, it's drawing power out of that wind turbine to control the torque and the speed of the wind turbine and get the maximum energy out with the minimum disturbance, the most benign way it can to the wind turbine. Quite a sophisticated bit of control electronics exists to control that power. Across on the other side here, we're collecting the energy and then we're squirting it out on the other side. Again, it's got to synchronize. And again, it's down to the power electronics to control the current waveforms that we're pushing out of that and to do it in the appropriate way for the grid. At a minimum, it's got to be synchronized to 50 Hertz. It's got to change its phase angle to be able to control the power. And it's got to react to a whole load of contingencies on this grid, such as faults, and do that in a way that doesn't damage the power electronics and acts benignly, helpfully towards the grid. It exists at monstrous great powers as well. For a long while, we've had a connection between the UK and France to link their nuclear power capacity into the UK grid. It runs under sea, and under sea, if you've got distances of about over 50 kilometres, AC transmission is really inefficient. It's all down to something called charging currents. A charging current is where the current you need to energise the cable. And a cable, when it's in the ground, looks like, as well as a conductor, a damn big capacitor. It's a little capacitor if it's a short cable, but it's a big capacitor if it's a long cable. And to charge that up and down takes charge out of that AC. Make it 50 kilometres offshore, you're starting to move almost as much charging current as you're moving real current. Build a transmission line. Now transmission lines are nice and up in the air, so the capacitance is small. The distance between the two electrodes is small, so if you remember your physics, so big, so if you remember your physics, the capacitance is smaller. It's about 500 kilometres. But even so, those are the kind of distances we're looking at shipping power these days. The reason we're interested in doing that is because we'd like to be able to pull renewable resources. We've got a shed load of wind, tidal and wave in northwest Europe. We've got lots of solar in the south. If we can pull those together, we can deal with some of the variability that you have in renewable energy and reduce the amount of infrastructure and storage that you've got. It's increasingly used in long-distance interconnectors, and it is big. Gigawatt scale, 800 kilovolts. And that's a real big challenge to make power converters that can do that, because again, we're talking linking two AC grids. We need DC in the middle, so we're going to have big DC to AC and AC to DC converters there to make it work. And automotive. Automotive has been touched on. Automotive is a little bit of a nightmare for the UK manufacturing industry, because we were good at building engines. We were good at building all the little mechanical actuators. We've now got a world which is going to depend on new clever electric motors, make them light, but a mass of power electronics. Taking from the way we go from our starting point, we've got an AC grid. We're probably still going to have AC grids for a while yet. You're going to have a grid interface. You're going to have a charge regulator, so AC to DC, DC to DC to regulate the current into the battery. Then you've got you've got the battery, and then you've got some kind of main bus controller here, possibly. Coming out of that, that's going to be about 800 volts, probably 800, 400 volts, depends on your vehicle. Coming through here, we've got a traction drive, up to about maybe 100 kilowatts. That's going to need to convert from DC on this side to the variable frequency AC to make that machine spin at the frequencies that we want, to control the torque in that machine to make it accelerate with the speed that we want. It's all done with power electronics. There's going to be actuators. Those actuators can be as simple as your braking and your steering. They may get really even more sophisticated as we move to complete autonomous driving. And then we've got a load of other stuff. At the moment, we've got all the low power loads, the lighting, the infotainment. In the future, we could be seeing intelligence there that's safety critical. And we're putting all of this on a power system, and all this power system is going to depend on these little power converters all working together to process power to make our little power system on wheels behave like a nice, safe vehicle. One of the big issues for here is we've got a twin dilemma. We're going to be adding lots of safety critical intelligence. We've already got safety critical intelligence in our cars. We're going to have more of that if we go for autonomous driving. And I'm going to be sticking a 800 volt, quite possibly silicon carbide converter, switching 800 volts, 100 nanoseconds. That's a massive dV by dt. A big dV by dt equates into fields being produced. Fields equate to electromagnetic interference. And we've started to put all these things in one enclosed chassis and on one power system. So we've got a nightmare for designers trying to make this whole thing work together and get the maximum use out of every component that we've got. So our nightmare, high EMI, safety critical systems. So how does power electronics work? We've got a switch. I've got a switchy thing. It turns on and it turns off. That's all it can do. But then that's what digital electronics does. We've got thousands and thousands of switchy things which turn on and off, and we put them all together to make really complicated systems. But here we're dealing with switchy things which control power. And a lot of it can be summed up in this simple circuit. It's not all of it, but for now we're just going to base it on one simple particular variety of power electronics. And that is two switches and a DC supply. As we saw in the other examples, a lot of the examples I gave you work from an intermediate DC supply. And that's why we're doing it this way, because it lends itself to relatively simple circuits. We've got a top switch and a bottom switch. If I turn on my top switch, I connect to the power supply. If I turn off my top switch and turn on the bottom switch, you connect to the bottom supply. Top switch on, I've got voltage coming out at the DC voltage. Bottom switch on, I've got 0 volts coming out. We don't ever turn those two devices on at the same time. Why? Because as we'll see in a slide some time later, it makes a nice bang. And we don't have these two switches off at the same time, except when we're moving between the two devices. We use it as a safety switching to avoid getting the shoot through. But what we can do is we can produce this voltage pulse. And this voltage pulse can happen many, many times per second. Slow in power electronics means 1,000 times per second. Fast means, well, fast in big machine drives, silicon carbide could be in the tens of kilohertz. In your little bitty converters inside your mobile phone, you could be pushing towards the megahertz range. But they all do the same. They're all producing this pulse, and because it's controllable, because is told what to do by electronics, I can change the width of that pulse. And by changing the width of that pulse, I can change the average voltage. And that allows us to start controlling power, because I've now got an efficient way of varying the magnitude of a voltage, vary the magnitude of the voltage, as we saw from our example with the oven, controlling the average. I can control the average current up or down as I control that. And here's where we start to get towards our converter. DC source, converter, bridge leg, a series of pulses that come out. And this is where things like this, my inductor, and things like this, my capacitor, start to come in. We don't want the output to respond to the high frequency. Like our cooker. Our cooker, if it ramped up to its maximum temperature and ramped down again, is not going to work. It relies on the thermal time constant to keep it smooth. Here we're relying on the electrical time constant of my system to smooth out the output. So we put in between my converter and the load some kind of filter. Now recall at the beginning I said my inductor, my windy thing, my copper round some kind of core, is an inductor. Inductor wants to impede the flow of high frequency electricity. So that's going to want to prevent this high frequency component passing through, but it's going to want to let the average pass through. So passing through that inductor, we're going to get a resistance to the high frequency bit. Now I put that together with a capacitor, and that capacitor is going to want to take the high frequency. That high frequency wants to find its way not out into the load or an additional inductor. It wants to go down this way here. So that takes away another bit of the high frequency component. And out of that side, what we'd like to get is the high frequency bit removed and an average voltage coming out of the output. So the filters there act to change the time constant of the circuit and act to allow us to use this high frequency waveform to change the average that we apply. Fairly simple. And here's some examples. So here's one switching waveform, and here's the output after the filter. So this maps into this. My voltage here is smoothed, but it's still got some ripple. And what can we do about that? We can switch it faster. By switching it faster, we now see we've still got some ripple, but it's much smaller. So switching is good, fast is good. Switching fast means a better approximation to what we want, in this case a controlled DC supply, or it means for the same voltage ripple I can make that inductor smaller. Why is making that inductor smaller? Great. This is big. Double the switching frequency, I can make this half the size. So it makes everything much smaller. So there's a big push to make things switch faster because it makes things smaller. It makes waveforms nicer, systems smaller. Great. Now, changing DC to DC is a bit prosaic. It doesn't let us make machines spin, it doesn't let us interface to the grid. What we'd like to do is to be able to generate a controllable AC waveform. And we can do that. So what are we doing now? My pulse width doesn't have to be fixed in time. My pulse width can change. It can be one pulse width at one sample instance, and it can get bigger and bigger and bigger, and it can get smaller and smaller and smaller. If we get that width to track a sinusoidal reference so that the width of that pulse is going up and down as the magnitude of that reference sine wave changes, so it gets bigger, it starts off small, it gets bigger and bigger and bigger, and it gets smaller and smaller and smaller, I can generate something that approximates to a sine wave. Now here is my low frequency one, and you can see with my filter there, it starts to approximate to a sine wave. It's not a good sine wave, but it starts to look like one. Increase my switching frequency, and I get something that looks quite close to it, certainly good enough to make a machine spin without too much vibration. Now the switching frequency harmonics, we'd like to get rid of these as well. Many times we can actually just connect direct to a motor, because a motor is an electromagnetic thing. It looks like an inductor, and it inherently smooths its current. If I switch too slow, I've got these high frequency harmonics. And if you've ever were sitting in an electric train, probably in the 90s, you'd have heard the thing squeak. Certainly we did on the locos that we built for Taiwan, and that's because the switching frequencies were making the windings in the machine actually vibrate, the machine vibrate a bit. So again, pushing up frequency is good, gets rid of the harmonics, gets rid of some of the losses in the machine, but as we're going to see, switching at high frequency brings its own problems. Switching matters. Switching matters a lot because it's our trade. It's one of the things that we can trade off. Switching high frequency, great. Filters small, control good, waveforms good. Better waveforms, smaller filters. Overall, the size can be brought down. It's particularly the case if we've got a DC to DC converter with a transformer. The kind of big growth for high switching frequency devices was originally driven by the aerospace, where they've got lots of DC to DC conversion. And high switching frequencies automatically made really tiny converters. But it adds to switching losses. The more often the device switches, the bigger the loss. The slower the device changes state, the bigger the loss. So if I've got a slow device, even if it's efficient when it's turned on, I can't switch it very frequently, sorry. So, my big friend here, probably technology from about 10 years ago, but we got given lots of them, so we're still blowing them up. That switches about 1 kilohertz. Pretty good, very, very good for its day, but we'd like to switch faster than that. Modern devices can probably push about 10 to 50 kilohertz. Fast switching times reduce losses. If I can get down from the kind of about microsecond with switching time with that IGBT down to 100 nanoseconds, I'm scoring probably about a 10 times reduction in switching loss. And that equates to efficiency. But it brings problems. And that starts to bring us on to some of the things that we've been looking at. So, we'd like to look at how these devices switch. And we'd like to do it at big voltages and big current, and we'd like to do it in the lab. But I don't want to be turning over tens or hundreds of kilowatts of power, because if I do that, I'm going to be burning a hole in the university's bank balance. So we'd like a clever way of being able to study scientifically how these devices switch. And when we sketched up, how long ago was it, Ross?
2 years ago.
About 2 years ago. This is our circuit diagram. Our rough sketch out, we've got a capacitor, the big brother of that's the size of a suitcase and weighs 25 kilograms. And we charge that up off of a power supply. Have we got anything more there? Yeah. We've got two devices. We've got a device that we want to test. We turn it on and off. And we've got a device which we just allow the current to freewheel through. What we do here, we charge the capacitor up from our high voltage but low current power supply. We disconnect it. We allow the capacitor to start building up current in that inductor. I then switch this device here several times, and we can control the voltage and the current that it switches at, and we can even control the temperature of the device with a heater plate. So it allows us to do very good controlled experiments. When we started building it, you need to start thinking about your device and the gate driver where that fits. You need precision probes. We've got 1 gigahertz isolated probes. It needs to be isolated because we're operating potentially up to 2 kV, and it needs to be able to measure at high voltages up to 1 gigahertz because we're switching the thing so fast. So we've got about £30,000 worth of test equipment wrapped around to see what's happening. You need to build a power assembly which is reasonably realistic of the power assembly that it might be seeing on a power converter, the kind of a commercial one. So it needs to have a low inductance bus bar, local capacitance, and down here we've got our power devices. We need to put in interlocks and protection. So the thing needs to go in a case, it needs to have things there to make sure no one can touch it, and equally importantly, it needs to make sure that everything powers up at the right time so that nothing explodes inadvertently. And by the time you put all that together, that little circuit diagram that we put, when you start to put all the ancillary electronics, all the safety features, all the blast shields in place and put the instrumentation around it, starts to take up the larger part of a lab. So that's our power converter sitting making bangs if you're ever in the Fleming-Jenkin building. And why are we doing that? It lets us get really accurate waveforms of what happens when the device switches. Here's a turn-off waveform. The blue line gives an IGBT, which is slow. The red one gives a modern silicon carbide device of about the same current waveform, current rating. And you can see here, this is the voltage across the device rising, very fast for the silicon carbide device, slow for the IGBT. And you see the same things for the current through the device. And this brings us to switching loss. Now, switching loss is important because switching loss tells me how much energy I'm burning in that device every time I switch it. So the product of current and volts gives me power. If I take those two together, I can see a small pulse of power dissipated in the silicon carbide device with a bit of ringing there, and a big pulse through the silicon carbide device. And you can see the losses are probably at least a factor of 5 down by going for that faster device. We see a similar thing when we turn the thing on. Again, look at the time bases that we've got here, and you can see the resolution that we need to get accurate waveforms of this. Here we're seeing the device voltage falling because it's a turn on, and it's heading down towards a negligibly small voltage from 600 volts. And here's my current rising. Again, we're seeing a massive reduction in loss associated with the silicon carbide device because the product of current and voltage is that much lower, and the energy, which is the area under there, is going to be smaller. But if we look carefully at both of these, we've introduced a new problem. Firstly, my edge is much faster. Edges generate dV by dt, generate potential interference. But worse than that, it kicks off oscillation. Very high frequency oscillation here. That oscillation, that voltage oscillation, that current oscillation is going to be seen in every little conductor that's associated with that device. Every little conductor that's in the air looks like an antenna. What's existing in the same world? You've got a gate drive, you've got a microcontroller just associated with the power electronics. Inside of those, you've got tracks. Those tracks are going to look like receptor tracks. So we've got a massive possibility of generating radiated interference, which can then be picked up by every other part of our system. The faster I switch this, and I could switch this much faster and get a faster edge and lower switching losses, the faster that dV by dt and the more pronounced and high frequency this oscillation. So we'd like to have some way of optimizing this. Is there a way that we can get the best possible switching speed out of it and minimize the oscillation? And we've been playing around with this. So what are we doing here? We're talking, and this hasn't kind of come out right, we've got a control node on my power device. 2 pins that tell it to turn on and turn off. But it needn't be a binary signal. I can vary the voltage that applies to this device, and here's the gate voltage here, and this is what we're seeing at let's get this right, a turn off characteristic. I'll just run this one back again. Is he going to play? Doesn't want to play. Come on. No. No. Anyway, you saw it. We can iterate this wave shape here. We can look at these waveforms, and we can do this quite nicely because we've got lots of expensive kit. And this simulation here shows us changing the voltage across here, and that voltage causes this to change. And as we change this, we go from this highly oscillatory behavior here to almost exactly the same switching speed, but we've got rid of these high-frequency oscillations. They're completely damped out without increasing the speed by very much. And that's one of the areas where we're looking at. We're confident that we can build a gate drive with that precision. We've built it. We've adapted techniques which are designed for signal processing, and we've got one of them working in the lab. We know that we can measure with these bandwidths. So in the lab, we can put this together, and we're pretty confident that we can make it work. The real trick is going to be to take this work and turn it into something that you could actually build. something that doesn't require £30,000 worth of test and measurement equipment to get the waveforms, something that doesn't require a computer running a iterative algorithm to come up with the best waveform. We can show that we can make it better. We can show that there may be waveforms here which produce optimized switching characteristics, but how do they change with current? How do they change with temperature of the device? Can we come up with something which is a reduced set of transitions here, which would actually be buildable at a reasonable price? So that's one of the areas that we looked at. Another area is things get complicated. I'm just going to give one example here. There's many others, but this example here is how do we operate at high voltages with limited device ratings? Now, why do we want to do that? I mentioned HVDC, 800 kilovolts. If anyone was paying attention, they'd have seen 6.5 kV as the maximum rating that we can get from a single switch. How can we possibly switch 800 kilovolts with something that only likes switching 6.5? You could put them all in a stack and switch at the same time. And TC, if it's here, TC, we spent a lifetime ago playing around in the labs at Heriot-Watt, taking IGBTs and trying to put them in series and getting them to switch, like one big composite switch, switching tens of kilovolts all at the same time. And you can do it, but it's damned hard work. So, other options. One option. This is some work we did in the past. This is looking at DC connection networks for offshore. Why are we doing that? DC is more efficient, and we're looking at building offshore wind farms. Also, we've got multiple conversion stages. Can we get rid of some of the AC stages, get rid of some of the losses in the cables, use smaller cables and work with DC? The problem is, lots of concept designs showed this, and they said, well, we're going to be we're starting off AC here, we turn it to DC, we turn it back to AC, then we turn it back to DC again at the other side. Let's get rid of some conversion stages. Yeah, it doesn't work quite as easy as that, because you need to get from about 3 kV maximum from your turbine. Probably going to be less than that. A lot of them work at lower voltages. Up to about 50 kilovolts to make an efficient collection network, to be comparable with what's done on AC at the moment. So you need to step up. How can I make a DC to DC converter go from 3 kilovolts to 50 kilovolts? And the trick we came up with was an array of converters, each one operating at about maybe 2 to 3 kilovolts, and using DC to DC converter technology, where you're generating a high frequency square wave and transmitting that power over a transformer and then rectifying it again to build up a high voltage. So you can be talking a combination of parallel devices on this side here and a combination of series devices on this side here to step up from 3 kilovolts to 1 kilovolt, while each of the power semiconductor devices is only rated at its optimal level. You can also do some interesting things because you've now built a modular structure, and you can introduce features such as fault ride-through and redundancy. The downside is you've got a lot of power electronics, and it requires the power electronics to become more reliable, and it requires the cost of that power electronics to come down before this type of approach is probably going to be viable offshore. It also increases the amount of control that you need. Now, somewhere where these kind of novel topologies have really taken off is in the area of HVDC. So we can reach about 800 kilovolts. How do we generate an AC output with a limited device rating? And this is what we do. Can you remember those bridge leg cell that I came up with? Device at the top turns on, voltage comes out of it, device at the bottom turns on, gets 0 volts. And we build up a whole series of these, each of which can switch in a little capacitor, and that little capacitor is holding charge, and that little capacitor subtracts some voltage from the AC. Each cell switches at a voltage compatible with a single device. So each of those ones there doesn't need to be high voltage rated. It's a little converter in all of its own right. You can get high efficiencies and good power quality. And why can we get that? The animations have all died. Anyway, no, right. Each of those switches as it turns on, will introduce a step. With all those switches off, I get one voltage state. With all of them on, I get to the other voltage state. I can step up and down between those. So each switch doesn't have to switch very often. By switching at multiple levels, I can build a staircase. To get 800 kilovolts, I'm not talking the few devices that I've got here, I'm talking hundreds. So each of these little tiny steps is going to be a small fraction of that. So you get something out of that with each device switches really, really, really slowly, about 50 hertz, and generates a nice smooth sine wave. And that, if you compare with what would happen if you built a 2-level converter, big series connected switches all switching together, and an MMC type converter, a modular multi-level converter, then you get this massive saving. You lose the switching loss because each device doesn't have to switch at a kilohertz now, it can switch at about 50 hertz. Downside is it's a complicated topology, not that complicated, nice and modular. People say it's complicated, it's just got a lot of switches in it. By the time you draw that as a block diagram, people don't really care. It does the job. More importantly, the control is complicated. Each of those cells isn't a voltage source, it's a capacitor. The capacitor needs to be supplied with the right amount of energy to keep its energy balanced. We need to balance the energy in all of these limbs to control these. And Michael, if he's about, Michael has spent probably a good number of years working with Alstom, coming up with the control algorithms that make this type of converter work, and building these into test converters that demonstrated the principle, not just of this one, which is the basic one, but of many other multi-level converters, all of which are designed to give different functionality. But it gives an example of how complicated these systems start to get. And there's other things that we're exploring, like I mentioned IGBTs in silicon carbide. Can we put them together in composite packs or composite converters, each to do a different bit of the work? It's a possibility. But there's not just research to be done in understanding the topology, understanding the devices, but also understanding how you can put the whole combination of devices, topology, control together to optimize a solution that does the right job at the right time. Come on. Lastly, things go bang. So that's our IGBT. I mentioned about short circuit tests. A requirement to commission our rig was that we had to demonstrate what would go wrong if everything went wrong. Would anything actually penetrate out of the blast enclosure? Would we cause any fire damage, etc.? So we were asked to conduct a series of controlled explosions. We don't want to blow things up. They're exciting, but blowing things up really, really isn't what we want to do. Each of these things, probably £100 a pop, so you really don't want to pop them too much. And that sort of ends the presentation, except I'd just like to show you something. So, again, this worked a minute ago. So, and so that's when you take 5.6 millifarads.
Told you to explode. It's right.
I'll play that again in case you missed it the first time. So this is what happens when we take that test rig. We take 5.6 millifarads of capacitance. Ross, can you remember how many joules that was?
Like 6 kilojoules?
About 6 kilojoules. So 6 kilojoules of energy being dissipated in a package about twice the size of this in about a microsecond. Make it a microsecond. And this is what happens to it.
Told you to explode. It's right.
Here's our library of various devices that we've blown up. They all had names before they exploded. So, one last play of the things going bang, because things going bang is quite exciting. So that's what it starts off as. This is one test that we did. This test is an overcurrent test through the inductor. So what we did on that one, if you can cast your mind back to the circuit diagram, I've got two switches, an inductor and a capacitor. Charge up the inductor and then switch them on and off. So this one here, what we did was we turned it on, charging, letting the current build up and up and up in the inductor until the thing went bang. And here you can see, because it's an inductor, you get a massive amount of arc damage because the inductor wants to keep the current flowing. So the device is really, really cooked. Here, we just short-circuited it. So it's taking the same amount of it's got the same amount of potential energy being driven through it, but is now on a capacitor. So nothing wants to keep current flowing, you don't get the arc. And you see this subtle difference in the damage. All of these things here, we blew the things apart, but all the safety worked. We didn't damage any of our nice probes, we didn't damage anybody, and apart from making some loud bangs and flashes, everything worked. So we're now on stream to be taking tests out of these things. And it's great because we can be running hundreds of tests per day, each with different, subtly different gate drive conditions, and we can start to get figures out for how these devices really behave at realistic volts and realistic amps. And that, at just over the hour, is me. Thank you very much. Any questions?
Okay, so I'd like to thank Steve very much for that very, very illuminating lecture. Certainly, I didn't appreciate the ubiquity of power electronics, and it looks a little bit like a pitch for a larger electronics department in the university, because it looks like no matter what we do, we're going to need more and more power electronics as the both the generation and the transport and the use of energy becomes increasingly electrified. So I think we've got some time for some questions. If anybody would like to kick it off.
Craig Sheridan from Edinburgh Innovations, and thank you very much for the presentation, very interesting. So I'll attempt to take you out of your academic comfort zone and contextualise my question around a marketplace. Electricity is becoming more of an exportable commodity. For example, there's a cable being built for that purpose between Scotland and Norway. So my question is, how can power electronics be used to determine who the winners will be in that international marketplace of buying and selling electricity?
I won't talk about the market. I'm not dodging the question because the market is just going to be set by the regulation. The big aspect that we can lose out on is if we become, as a nation, region, whatever you want to call it, a net buyer of the technology. If we don't manufacture this kit, we're going to be buying it in. So it doesn't matter what the trading regime is. These things cost about £1 billion a pop, plus the maintenance contracts. So if we're going to want to transmit power across to Norway, if we're buying that from Mitsubishi, ABB, GE, you can debate, they've got a presence in Stafford, but if we're buying that in, we don't benefit from any of the vast wealth that's going to be generated in terms of jobs and profits from this infrastructure investment. We're just going to be investing in it. And the people who own the wind farms, they're going to be benefiting, or wind farms or the dams, they're going to be the ones that benefit. Depends on your tax regime. So the market benefiting really depends on the ownership and tax regime. Profits out of power electronics depends on us actually making an industry in the sector.
Another question?
Assuming that power electronics will follow suit with digital electronics, very soon there will be increasing legacy issues in a system that has to work in sync altogether, reliably altogether. So design decisions and implementation decisions made at the moment will have dire, well, maybe not dire, but for sure some consequences in 20, 30 years. So what do you think is a way to mitigate that, and what do you think that the biggest threats are?
Well, there's two elements to the threat. One is the threat of not having compatible devices. So if you've got legacy equipment you need, and the types of device that you're making, if you want to have systems which are maintainable, you need to make sure that there's legacy devices which are compatible with that. And that can mean even that a device which is nominally better might cause problems. In terms of the system level problems, some of that is mitigated by the fact that so much of it relies on software. That in many cases you could take, say, a converter that is designed to give a particular response, say, to a grid fault, and it could be a relatively simple change to adapt that in terms of the software to make it behave in a different manner. And that was done, I believe, in Europe after the big cutouts about 10 years ago, when they changed the fault ride-through characteristics of many of the wind turbines. But yes, it's an issue, mitigated partly by ability to update the control software, ability relatively quickly to change the converter without having to change the full system as well. But yes.
Okay, thanks, Adam. Another question?
Quick written supply design. Power electronics covers a vast range of skills from digital control theory, sensor design, understanding how to use sensors, control of large silicon devices, magnetics design, thermal design. Where do we have the biggest shortage of skills in the country? Where should students and people who want to get into power electronics, where should they focus? Should they be generalists? Should they be specialists? What should the university be teaching to?
Ideally, I'd see someone coming through is somebody who has done a pretty general first degree, a kind of standard either electromechanical or EEE degree program that's exposed them to aspects from machines through to electronic control, and then either to spend a stint working as a junior in a design house or to do a PhD. Because I think that's the only, really, you've only got a trained power electronics engineer after they're about 3 to 5 years out of the university. We can teach them the basics. We can hopefully enthuse them about the area, but it is in such a it's not perceived as being multidisciplinary, but it is multidisciplinary area that you can only build it up with experience and hands-on. The biggest problem I see is getting the people who are keen to make the first leap from the more defined aspects of electrical and electronic engineering into power electronics. I'm not sure why that is. I find it fascinating. Maybe it's hard, maybe it's obscure, but it's certainly a growth area for jobs.
Maybe time for one more question. No? One more on the right there.
If most of our power generation and transmission is going to be mediated through power electronics, is there any strong reason in the future to keep a 50 hertz system, or should we think about changing that?
Huge area of debate. The EPSRC Supergen program, nigh on, we pushing 15 years ago, was debating that. In theory, you can make a system that works purely on power electronics because you can control it fast. The problem is trying to integrate that with something which has got a legacy, and that legacy is based on certain control principles, and trying to get the behavior, the fault ride through the protection characteristics of something which is power electronics based to look the same as a 50 hertz system based on large rotating plant is a huge challenge. And given that we're not going to use the nuke plants probably at the rate that we're going for another 10 years, we're stuck with this intermediate world for a while. To give you an idea, you could a big American warship, probably 50 to 100 megawatts worth of load on it, all power electronic connected. It's a power system, and if you're going to spend that amount of money on it and you can sensor it up, you can make it work. You could theoretically apply the same kind of thing to an overarching power electronic based grid and make it work if you were starting from scratch and had full design rights over it. But trying to make the two systems work together is a big challenge. A lot of work being done if you look up on, what's it called, virtual synchronous machine, trying to make power electronic based converters behave like a synchronous generator.
Okay, excellent. So let's show our appreciation again to Steve for what I thought was a very accessible and a very interesting lecture, which really demonstrated the application and importance of the area of power electronics.
Thank you.